Imagine a highly anticipated sneaker drop or a blockbuster concert ticket release. At the exact same millisecond, tens of thousands of users across the globe click buy for a single limited item. This is the high-stakes environment of modern concurrency. To bypass that hardware limit, engineers moved toward horizontal scaling, or sharding. Instead of one massive supercomputer, the database is split across a vast global network of standard commodity servers. However, this creates a new bottleneck. Applying strict ACID locks across a globally distributed network forces servers in different continents to constantly pause and verify each other's status. The time required for those servers to communicate brings the entire system to a halt. To build the modern internet, database engineers had to prioritize absolute speed over the restrictive safety of strict transaction locks. It was a choice that made concurrency chaos an inevitable part of the architecture. This led to a new set of rules known as the base model. It prioritizes systems being basically available, maintaining a soft state, and settling for eventual consistency to keep data moving. We can see this in action within Apache Cassandra, a database built on a masterless, peer-to-peer architecture. In this system, every server node is identical and can accept incoming writes. Because there is no central gatekeeper, two users in different countries can write conflicting updates to the same record simultaneously. Inside the database, every column contains 3 elements: a name, a value, and a digital timestamp. When conflicting packets meet, the database uses these timestamps as a tiebreaker, automatically overriding the older data with the newer timestamp. Developers can also use tunable consistency. They can choose whether a specific query needs agreement from just one node for maximum speed, or a quorum of multiple nodes for higher accuracy. Distributed databases survive global traffic spikes by allowing these collisions to happen and using time itself as the ultimate resolution. But data collisions aren't the only threat. If a server sparks and goes dark mid-write, a traditional system leaves that critical data in limbo. Document-oriented databases like MongoDB handle this hardware failure using an architecture called single master with replica sets. Normally, a primary node handles write traffic, while secondary nodes replicate data in the background. If the primary goes offline, secondaries detect the loss, hold an automated election within milliseconds, and promote a new primary to resume data flow. By automating this leadership change at network speeds, the system renders catastrophic hardware failure invisible to the end user. Some collisions happen entirely outside the reach of the network. Imagine 2 field workers in rural areas losing connection at the exact same time. While offline, both workers modify the exact same customer record on their tablets. These changes are saved locally on each device's mobile database. The conflict occurs when both workers return to a Wi-Fi zone. Their devices simultaneously upload 2 different versions to the central server. These systems use a synchronization communication gateway to reconcile the mess. This software layer intercepts the uploads, runs conflict resolution algorithms to compare the changes, and merges them into a single, accurate record. Mobile architectures isolate this chaos at the edge of the network, pulling the resolution off of fragile local devices and handling it in a secure, centralized gateway. In the early days of computing, databases were treated like fortresses. Engineers built strict locks and rigid schemas to keep chaos from ever entering the system. But on a global scale, the speed of light creates unavoidable latency between data centers. Waiting for every server on Earth to agree would slow the internet to a crawl. In high-traffic systems, the cost of absolute certainty is a total loss of availability. Modern architectures have adapted by embracing the flow. By using eventual consistency, using embedded timestamps, and automated replica elections, they allow data to move without interruption. Modern reliability depends on the system's capacity for constant background self-correction. Instead of attempting to block every possible conflict, the software reconciles them as they occur. These architectures favor fluid resilience. They are built to absorb millions of individual conflicts and silently weave them back into a unified record, maintaining perfect order without ever needing to pause.